The big idea of Chapter 12 is doing a linear regression inference test, which if you're using your calculator, you can help it. You can help by doing linear regression t-test. I believe if you want to look for that in your calculator, you can find some information on that. So we're going to start with a problem, and I'll show you the basics behind it. So, do customers who stay longer at a buffet give larger tips? Charlotte, an AP statistics student who worked at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes the party was in the restaurant and the amount of the tip in dollars. Do these data provide convincing evidence that customers who stay longer give larger tips? Here are the data. So I've got the time in minutes here, and I've got the tip value over here. So I want you to pause this, and I want you to put this into a spreadsheet on your Inspire. And part one is I want you to graph the scatter plot and state the least squares regression line. So I'm pressing analyze, menu, analyze, regression. You could also do this from the spreadsheet. There's linear regression, and keep in mind we do it in this A plus BX form is the way we keep using it. So when I'm doing my least squares regression line, up is popping up something like this. So take a minute and make sure you're getting this information. I'm going to go back to my spreadsheet where I also did linear regression. I believe I called it BX plus A or something, A plus BX, something like that. And you get a few pieces of information. They give you A, 4.53497, B 0.03013. They give you R squared and R. I don't know if you remember the R squared or what the R stands for. R was like your strength of your line. So if you were straight up increasing, something like straight increasing was a +1, straight decreasing was a -1, and then we gave values in between. So this one isn't a +1, it's about 0.3. So it's kind of what we would call it like a weak relationship between the two. We'd say like a weak positive. Linear association is how we would word it for something like that. There's our least squares regression line. We would probably put predicted value. I think we used to put on all these Y's was the hat for our predicted value. And you want to make sure that you explain what variables you're using. Y was the predicted tip amount, and X was the length of stay. Interpret the slope and y-intercept of the least squares regression line. This is all pretty much review from the previous chapter. I want to say chapter 3. It was a long time ago that we did something like this, where you're trying to interpret a slope of 0.03. So keep in mind what that's standing for. X is the length of stay. So this is 0.03013 over 1. And the way that I kind of would word this is for each additional 1 minute. So basically, like per 1 minute, the least squares regression line predicts that the tip will increase by 0.03, which is really 3 cents. Something like that. Another thing is talking about the y-intercept. For this one, my y-intercept is like 4.5. So what is that meaning? Technically, if you put a 0 in for the length of stay, that would mean they're not there ever, that you're going to get a tip of $4.53. So that's not really part of our data that we're using. Our data starting around here. So when you're out of the realm of the data, you call that extrapolation. So you might want to put on here the y-intercept. And this is all stuff, this is all very much review. Means that a person who stayed 0 minutes will tip $4.53. And you might want to put something about extrapolation. The main thing is the new stuff. On the next page, I want to put some new stuff. Carry out an appropriate test to answer Charlotte's question. Now go back and look at what her question was. Do these data provide convincing evidence that customers who stay longer give larger tips? So we're going to do the same type of test as we were doing before, but be careful. We're doing this linear regression t-test. We're not really dealing with proportions here. So we're going to be doing a t-test. Before we can even start, there are certain conditions. Now, before our conditions were random, normal, and independent. And they're very similar over here as well. Random is standing for the R. So you're still looking for, does the data somewhere say random? And I'm checking it because I believe I underlined it on the last one. Independent is also still here under the I. That's that 10% rule. So look back at the question. She took a random sample of receipts. She has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 receipts. Seems like that was her job, so I'm assuming that 12 receipts is smaller than 10% of what she has had previously. Normal is also on here. And for normal, what you're trying to look for is the probability plot of the residuals. So if you would take a minute and see what the residual plot was. When I look at this data random data. We don't really want it to look curved or anything like that. So we're trying to assess the data based on this normal section over here by saying, okay, is the probability plot of the residuals, does it look like it has a pattern? We don't want it to. We want it to be no pattern at all. So some new ones that we're going to add in. Let's see, L is standing for the actual word linear. And what we're going to look for is scatter plot, seems linear, and you can also examine the residuals, centered at 0. What you'll notice is oftentimes you're going to be given a picture of the residuals or a picture of the scatter plot as well to be able to use from that. And last but not least is E, and we're looking for equal variance. And again, scatter of the residual or the residual plot. And it should be above and below 0 is roughly the same. And those are the conditions prior to being able to do a linear regression t-test. Let's look at some things. Okay, a couple things that I want to make sure that we talk about is this is the regression line that we've been using, the population regression line, and the reason we're using T is we're using the mean of Y, alpha, beta, X as our population. This is going to be our predictor. This would be your actual. This would be what your what the population would be. So that kind of might help a little bit. For these linear regression t-tests, it's all dealing with slope. Slope is the big idea there. So we're going to only be testing for slope and seeing, because when we look at her question was, do these data provide convincing evidence that customers who stay longer give larger tips? So if they didn't, our null hypothesis would be that there would be no slope. They would stay a very long time and their tip wouldn't increase. What we're trying to see is, would their tip increase? We need the slope to increase as well to try to test this. Your test statistic, I bet you probably could come up with this by using this data, but I'm going to put it down for you. B was 0.03. So this B is actually that 03013. We're testing to see if the null hypothesis is true, where beta equals 0. So we're going to put a 0 in there. For the standard error of the slope, if you do a linear regression t-test, there's a column where out will come B, I believe. Beta won't come out there because you're testing what the beta is. Standard error slope is 0.024481. So I'm going to calculate it like this for now and see what we get. And what you'll notice is your calculator will actually spit out the t value and the p value as well. When you take away that, you end up with this over this 1.23. is our t value. Now, the tricky part with this is that your degrees of freedom for this is n minus 2, not n minus 1. So we've got, 12 minus 2, you're going to be looking up in the t chart. For degrees of freedom is 10, and the t value is 1.23. So when I look this up, I'm getting a p value of between 0.15 and 0.10. If we're looking in our calculator, p value it gives me is 0.123 within there. So it actually gives me my p value. Oftentimes we're going to be looking at this mini tab outcome at the end. So I'm going to fill that in as well with some things that you might not be asked to put all this in your calculator. They might give you information right off the bat. What I want to show is that the SE formula is a little bit complicated. I said I would show it. It's S over S of X square root of n minus 1. Now where all these other information, where S comes from and S of X, again, there's more formulas for those too. Get what the S value is, which is 1.77 from the calculator. And the S of X, two variable statistics, and got the S of X, which is like 21.9. And then I square rooted n minus 1, which was 11. And out came the 0.2. It came out to 0.025 when we know it's supposed to be 0.0244, something like that. That's where that's coming from. Personally, you can steal all this from the calculator and be able to calculate it. You also get the t value and the p value of what the actual p value will be. Since the p value is greater than alpha, we failed to reject the null hypothesis. We do not have convincing evidence that parties who stay longer at buffets leave larger tips, something like that. What I've noticed is when I'm trying to do practice problems at the end of this section, you might not be given all this information. So you might be given information in a mini-tab output. So hopefully you'll start seeing where all these numbers are coming from. You might be given information like that. 0.03013, 1.657, 0.02448, 2.74, 1.23, 0.021, 0.247. S equals 1.779, R squared 13.2%, R squared adjusted 4.5%. So take a look at the information that may be given to you in kind of an output. You got to be able to read these. Your coefficients here for your constant and your time in minutes. So this would be your A and this would be your B. Your standard error coefficient, that's where your SE coefficient came from. Your T value. Now be careful because look at what the P value would be, and that should be P above this, like here, instead of there. The computer output that will be given to you will be two-tailed. So it will be giving you that for here to here and here to here is 0.247. What we were testing for is to see the greater than, right? We wanted to see if the slope was going to be bigger than, so you'd have to have it to get 0.1235, something like that. That's where that 0.123 is coming from. So be careful, because the computer, not our computer, but if they give you a Minitab output, it would be something like that where you'd have to have it if you want only one part of the tail. There's your S value, your R squared. The reason it's a t-test is because we're doing the means. Okay. As far as the conditions, what you're looking for is you're really trying to make sure that there's no obvious violation. Minor ones are just going to be kind of overlooked, but no obvious observations.